literally. Okay. So I know most of you guys went to. I know you mostly no, all of you guys I think went to Prash's crash course, right? Oh, oh shit! Wait, how far are you along with concrete, Josh? You're up to date. Oh, okay, great. That means I can go through the first bit a bit quicker. Because my last session with like the third years, they weren't able to attend Prash's crash course, so I had to spend longer talking about the testing stuff, right? But I'm gonna just try my best to keep it to explain things that he didn't explain that much. What? Okay. All right. So first we're gonna start with hardened concrete, and then reinforced concrete, and then I especially want to emphasize for you guys design, because you guys, unlike the first group, you haven't done steel structures, right? So you're gonna have to learn the design stuff from scratch, which is fine because it's not that hard, but it's the first time when you learn it, it's completely new. It's different to like the other type of maths and stuff that you've done, essentially. Okay, so I'm going to go over this quickly because Prash went over it mostly, right? The direct tensile test, that one's quite difficult to do because it's hard to grip onto the specimen, right? If Sita knows what's going on. The splitting test, that one's like the knife's edge test. It looks like a compressive test because you're pushing down on it, but these pieces will come apart in a tensile way, right? And the flexural test is the one that's done on an actual beam. It's probably the most elaborate setup. This one that I've drawn here is a 3-point test. I've got one down below that's not, but the stress distribution is more accurate to what you'd see in an actual beam in real life. So this one's probably the most like realistic simulation of what's going on, essentially, right? I also want to note that like the testing that you've seen probably in high school for like physics, chemistry, that kind of stuff, it's all educational kind of tests and labs that you've been doing. But these kind of lab tests, it's because concrete varies so much. There's so many different types and batches of concrete. At the end of the day, what we want is to find out the material properties, the mechanical material properties of that batch of concrete that you've just invented or whatever. And you have to justify it through all these testing means and stuff like that, right? Yeah. So there's like Australian standards and stuff for testing, essentially. Okay. So does anyone remember why a 4-point test might be advantageous over a 3-point test?
Push it down on one point.
Yes, so basically for a 3.1, we're just focusing on that middle section. We're assuming that middle section is representative of the entire beam. But as we know, concrete will vary along the beam. The section might look slightly different because there might be micro fractures in the ceramic fabric, essentially, right? And so what's a better test is the 4-point test, because this entire area of uniform bending moment is going to be tested all at once, and then the worst possible point is going to break, or the worst possible section will actually be the part that breaks. So some tests you might see it might split here, some you might see it split there. Yeah, it's just a better and more representative type of test, right? Okay, I'm not going to go into this much because I don't know that much about shrinkage, but you remember this from your assignment when you tried to do it, right? Shrinkage is really annoying. It's basically, the general definition is a reduction in volume, right? But it can be due to moisture loss. So in the fresh concrete stage, so as the concrete is still setting, this is called plastic shrinkage. Once it's already hardened, that's called drying shrinkage, right? But overall, it's due to moisture loss from the surface, because water evaporates usually from the surface, right? Well, from the surface. Okay, but due to the hydration reaction of the cement, that's the cement reacting with the water, sometimes you get chemical shrinkage, right? So there'll be a reduction in volume due to that chemical reaction that's happening. And self-desiccation is a type of shrinkage classified as an autogeneous shrinkage that results in like an internal drying. So instead of the drying happening from the outside surface of the concrete, it's actually within the meat of the concrete. That's where the drying is happening, right? Kind of make sense? I'm not going to go into any more detail because that's pretty much where my knowledge ends with the chemistry / material stuff, right? Thanks, Subsida. Okay, reinforced concrete, yeah? So why do we reinforce concrete in general? Why is it such a core part of this course? Because in the steel design course, the 33031, that's run in term 1, we just work with steel. We don't need any other material, but for concrete, we need to reinforce it. Why is that?
Because it's really weak in tension.
Essentially, yeah. You're right, and that's the main reason. So, you can see this is the material curve. If you take this, the down part of this material curve as axial compression, and the up part is tension. Basically, concrete is 10 times weaker in tension than it is for compression, right? One example I went through with the other group is imagine like you have a ceramic bowl, right? Looks like this, and you have it right side up, and it's made out of ceramic, right? If it's pushed against the surface of the ground like this, and you put the point force, say it's my hand or something, or my foot, and I'm stepping on it, that's a compressive load, essentially. And it's not going to break, essentially, right? When you have the bowl right side up. But if you have the bowl flips upside down like this, right? But if I do a little X-ray into the bowl, essentially, there's nothing suspending it, right? And I apply that same load on the top. It's potentially going to break if I put enough load onto it, right? This is essentially like a beam, right? So it's gonna bend and cave inwards like this, right? Gonna bend and cave inwards like this, and the bottom point is gonna be in tension, right? That's where it's gonna fracture. The cracks will propagate, expand, and then the whole thing will break, right? So that's basically concrete or any kind of ceramic. If we look at the individual components of concrete, right, on the right here, these are the stress strain graphs of the individual property, the individual ingredients, right? So we have the aggregate, which is the rock. You have the paste, and then concrete is when everything's mixed together, right? So the aggregate is very brittle. That's like the rock, right? It's going to break very suddenly. So it doesn't really have a tapering off or anything like that. It just suddenly snaps and boom, it's broken, right? But it's really strong. That's aggregate. It's really strong and it's really stiff. Stiffness is the slope, right? The elastic modulus that represents the stiffness, right? Paste, you can see the slope isn't as high, so it's not as stiff, right? It'll basically move a bit more for the same amount of force applied to it, right? And it's not as strong either. You see how it starts plateauing faster, and it has this softening behavior like this, right? That's called plastic behavior, so that's paste. So when you combine concrete and paste together, aggregate and paste together to make concrete, turns out the stiffness is right in the middle. The slope is in the middle between those two ingredients, but the strength isn't as high. So why do you reckon that is? The max, it's called like, so this one's FC. Compressive. The aggregate one is actually the strongest, and then the paste.
I thought it was the ultimate.
This is essentially the ultimate, yeah, because it's at the point just as it breaks, right?
It's like the average. Is it not? It's like
Sorry.
the average of aggregate and paste.
Oh yeah, the stiffness. Yeah, the slope is the average, but do you see how the concrete doesn't actually go as high as the paste in terms of the max number it can go up and down?
Oh.
So why do you reckon that
does it
is?
have a plastic region?
It has a small plastic region. Paste would have a bigger one. The plastic region is how much it tapers off and softens at the
Does
end.
it have an elastic region?
Yeah. The elastic region is the linear part, right?
Oh wait.
So why do you reckon it's not as strong as paste by itself, for example?
Because paste
It's
is a lot.
probably to do with like
Paste is more workable.
the interaction between the aggregate and the paste, right? Like the borderline. Like
Yes.
when we went to
Perfect,
in
perfect,
maths
perfect.
101, it's like
Perfect,
it like
perfect.
stretches like the breaking or whatever.
Yeah. I'll show you. So here's a little section, right? If I zoom in, if these are the rock particles, the aggregate, right? And everything in between what I'm drawing is the paste, right? So the blue part, for example, is the paste.
Slipline.
Yes,
There we go. That's the word I'm looking for.
Where it will break is this. It's called the, I think it's IZP, inter something zone. IP. IF is What?
ITZ.
ITZ, yeah. What's the T part?
So, oh, sorry.
Tensile zone.
T is
Anyway,
tensile.
it's something like this.
T is tensile, and then Z is or
I remember reading this in your notes.
inter something zone.
Interfacial tensile zone.
Tensile. It was tensile. Zone.
Yeah, interfacial tensile
I
zone.
remember
Yeah.
reading your final step. I was like, what the hell is ITZ?
Oh yeah, it's that. Basically, that's an important property of concrete. The way that Janice explained it was it's like an Oreo. So the cream and the Oreo come apart when you pull on it before the Oreo splits apart. You know what I mean? Like the brown bits of the Oreo aren't gonna just come apart when you pull the Oreo. It's gonna be the interface between the cream and the brown part of the Oreo. That's why, basically, right?
I get it.
Yeah. And the paste failing would be the equivalent of, in this Oreo scenario, it's splitting right in the middle of the cream.
Oh, so like the cookie
This
part.
is the aggregate.
So that's the Oreo.
I get it now.
And that's the, so it comes apart, it always comes apart here, right? It doesn't come in the apart in the middle. It's rarer though, right? So this is the same thing that happens with concrete.
I think the only time it really happens is when your cream is slightly melted.
Yes, you are doing Oreos.
Fine.
If it's slightly more melted, it means the cream is more ductile.
That's like heat.
Yeah, due to heat and stuff,
Temperature.
right? Okay, anyway. We're gonna move on, right? Okay. So okay. Well, one important thing is that, okay, just keep this in mind, yeah? If I have like a bowl, right? Actually, if I have 100 different bowls and I dropped it from the same height like this, say some of them break and some of them don't break, right? So why is that? Like if I have the exact same apparatus where I drop it from the same height, same angle,
Some of them are more sigma than the others.
Just unlucky, I guess.
It's unlucky.
Well, isn't it just like depending on like
What's different about all of these bowls? Say they're all IKEA bowls.
aren't they all the
Maybe
same?
some of them have impurities or something. Like it's not
What kind of impurities?
like holes.
Yeah,
Wait,
that's
It's
right.
ceramic, right? So
Yeah.
like,
Yeah, they're called microfractures. But you're exactly right. The microfractures are gonna be points which cracks can start propagating from, which is just growing, and then that's where the weakness points are, essentially, right? So some bowls will have more than others, just due to, like ceramics are just very highly variable materials. So if I draw on the board or something, if you zoom into a little bit of a bowl, you're gonna have microfractures and stuff like this, right? Yeah. Anyway, but if you plot, say like, this is the probability that it survives if I do that drop test. And say I like have 1,000 bowls that I tested this with, right? It's gonna follow a random distribution curve, right? Normal curve, right? And this is, let's call that the strength, the compressive strength, let's just say, right? Okay. Actually, compressive strength, we're gonna say that it's from a compression, it's gonna be from a compression squash test, right? So why would some fail here and some fail up here?
Depends on how the microfracture.
Yeah, exactly. Yeah. There's like a million reasons, and it's on a microscopic level, essentially, right? But this middle point here, this is called the FCM, the mean compressive strength, right? Would we design for the mean?
maybe a little bit higher.
Would we design for here? So we're pretending that it's a bit stronger than the mean. If we're designing higher than it, right?
Wouldn't it be way more stronger?
We're designing for, so you want to design for something that's way stronger than it actually is, on average?
Just a little bit, right?
A little bit stronger. So okay, let's take another scenario, right? You're designing scaffolding for 3 tradies, right? And say they're really heavy, say they're like 100 kilos. So 3 heavy tradies. Are you gonna design that scaffolding to break at 300 kilograms?
No, you're gonna design it to break at 350 kilograms.
So does that mean you're assuming the material is stronger or weaker?
got-
weaker than what it
Yeah.
actually
So you wouldn't actually want to design
Oh,
it
you
too
want to go
strong.
that way?
Okay, so how far left would you go?
Maybe a little bit more.
Based on your feelings.
You're interested
But they
in
have to have a standardized way to do it. Would you do the worst case scenario?
No,
No.
Why not?
that's just so extreme.
But like nothing will break instantly.
Yeah, so there might be a defect.
Yeah.
So you test 1,000 bowls. You don't want to test for the 1,000 weakest. Strongest. Yeah, 1,000 strongest, right? So which one would you design for? What's like a good balance point? 750 out of it.
5%.
It's five. It's the 5th percentile. So it would be the 50th. From the bottom. So the 50th out of
50th from the
1,000.
bottom, sorry.
50th.
Yeah.
I just thought
Halfway.
50, you said 50th and I thought 50%.
So this is the 5th percentile value. This is what we designed for. So this is called the characteristic strength, right? So whenever you see the dash, that just refers to it being the 5th percentile one, because they could write F, C,
And then
comma,
M or-
5th, but it's cleaner just to write it as a dash. So whenever you see a dash, that means they're referring to that 50th from the weakest in the 1,000. Yeah. Anyway, yeah, right. Okay. So in order to find this, right, in terms of the statistics and probability and all that shit, if you're doing 2002, we have to go one margin down, right, from FCM to F-C. So that margin M is 1.64 standard deviations, right? Right. So you have all your data in Excel. You can calculate what the standard deviation is, right? And then you can get that value, subtract 1.64 standard deviations, and then that gives you the characteristic strength, right?
66.8% of the entire graph. 2 standard deviations would mean it's 95% of the entire sample.
Yeah.
3 standard deviations is 99.75. Well, 99.7%.
This is why I don't know.
This is
I don't
advanced
remember.
math.
Yeah, I don't remember. This is why I can't remember.
Let's do your math.
But the good news is you don't really, you just need to know where this comes from, but you never need to touch it again for the
You
rest
just
of the
need
course.
the number, right?
You don't even need this.
Oh.
You don't do any probability in this course. Everything's deterministic. But they've already calculated it for you.
1.645.
You still don't even need to do that next course.
1.64. That's the test.
Okay, to give you context of where we are in the
That's
course,
an S? Oh, yes, this is an S.
to give you context of where we are in the course, do you know how in year 11 and 12 they teach you calculus, right? And then there's pre-calculus, that's like limits and shit. That's what we're learning right now. We're not even doing the proper calculus part or equivalent of it. This isn't the meat of it yet. They're just telling you where everything's from.
This is a formula, like the derivation.
It's derivation, but it's like testing based kind of derivation. Yeah. Okay. So another term to get yourself familiar with is FCMI. What do you think FCMI means?
The guy just talked about this today. It is the in-situ compressor.
What is this? What is it? What does
Well,
institute mean?
Thanks.
Inside.
No worries. Inside.
Inside of the concrete.
Sure.
So it is the strength of the concrete as it exists or its place in its final position within a structure. That's what this
Yeah.
guy
So I
said.
think institute might be Latin or something. So do you know how concrete's poured?
It's board.
It's poured on site. So institute just means on site. So when it's poured, okay. So basically, say you're baking a cake, right? This is actually you find so many similarities between baking a cake and fucking pouring concrete.
Inside of the concrete, you pour it inside of the tin as opposed to outside.
So you just poured it in the tin, right? Like your cake mix and shit, and you just chucked it in the oven, and then you test how strong it is. That's the institute strength. After it's done baking, that's your main strength, or it's called the 28 days strength.
Yeah.
It's because you wait exactly 28 days, right? And these are standardized Because
Why didn't you wait any longer, Professor Zhang?
Okay, I'll tell you why.
28 days is like when it's like
The peak. Yeah.
most effective time to effective strength.
No, it's because you have to put a cap on it eventually, right? So I'll show you how concrete grows in strength over time, right? So say we're just analyzing the compressive strength, and then this is over time, right? Concrete looks like that, and it keeps plateauing. I like to write that, like that, right? So at here, this is 7 days. It keeps growing very quickly until 7 days. Here's like 28 days, and then past that, there's a marginal difference in terms of how much stronger it's going to get, right? Does that make sense? Yeah. So they standardize it at 28 days because if you just don't have a limit, right? It's not really standardized. Like your batch could be a different strength on one day and CLO and stuff like that. So they just cap it at 28, right? Okay, cool. So, I was like after I did the lecture bash for PDC with Kaiten and Dave, I just sat in the lecture for a little longer and I was watching Taewon like go through all these formulas and I was like, only one of these actually matters, right? Like I was telling Kaiten, right? And I'll tell you the one that does matter. So remember, these are all your different tests and stuff, and it's how they relate to each other. So some will be exaggerated, some will be like, yeah, the flexural test will be like 1.67 times as much as the strength from the direct test, etc. But the only one that really matters is this one. This is the splitting test strength, like tensile strength. Sorry, not splitting. The flexural tensile strength test. And there's a correlation between it and the compressive strength. So why do you reckon this would be important? This particular relationship? It's empirical, so it's from a lot of test data. And it's also specific to the Australian standards. So you'll find a different one in the Canadian standards, you'll find a different one in the fucking Mexican standards, one in Jamaican standards, I don't know.
Because of the different like environments that it was tested in.
Yes. Yes, that does actually affect it, and like
all the different things that could affect the actual.
Yeah, no, you're right. You're right about that, and like why that's slightly different in all the different regions. But why is the relationship there? Like, why do we care about this relationship? Do you reckon? To begin with, so say these numbers are slightly different in all the different standards, but why do we need to relate the flexural test strength in tension to the compressive strength? Well, compressive strength is the easiest test to do, right? Do you know how we're talking about all these different types of tests? Those were all the tensile ones, which are hard to do. The compressive one's trivial. It's literally you get like in Minecraft, like pistons, and you push them together, right? It's a hydraulic press kind of test. It's incredibly simple to do, and you actually have to do those compressive cylinders for every structural pour you do on site, right? So you're gonna have to do this test a lot, and like companies get paid to do this test and stuff. But the reason why it's important for the flexural tensile test is when we're doing beam design, all the numbers are based on its flexural strength, right? You'll see this play out properly next week. But when we do all the calcs, we need the material properties for how strong it is in tension, but specifically in bending. I'm gonna give you a bit of PTSD from solid mechanics, right? Do you remember this shit? Euler's beam theory? Basically, it's saying this has to equal FCTF. The tensile fiber, the outermost tensile fiber, has to be that strong or whatever in the design for it. Yeah? And that's the stress distribution. Okay. So basically, this one's easy to test for, and this one's useful for design. That's why this is the most important material relationship. So in a lot of questions, you're going to get, it's going to tell you, oh, the concrete strength is FC is equal to that. Then you're going to need to plug in this formula, and you plug this one into the equation sometimes. Yeah. Okay. There's also a correspondence, the correlation between elastic modulus of concrete and its density and all that shit. But again, this will never come up again in the course. I think it will come up in your workshop, but it won't come up in your fucking final exam. Yeah. These are all empirical relationships that they've found for Australian concrete, basically, right? Okay. You guys want a break?
Yeah, one more.
Well, I want a break, so we're doing a 5-minute break.
He's been yapping for 1.5 hours.
I need to go to the toilet.
Can I follow you? You didn't even let it wait.
No, because it straight away goes to voicemail.
Oh.
It's twice.
I can see Farhan about to FD this and HD this course again. Inshallah.
Did you already say it?
I didn't have to, I just started singing.
No, because does your, it depends if your you use that pencil.
Yeah, it's still compatible.
Or do you
Yeah, I just accidentally bought the wrong one. I accidentally bought the one that's
the old one?
yeah. I just think about it. How does it work?
It just bent backwards. It usually just sits once you pick it on.
You weird, yeah.
I learned that the game. Well, I am the, I guess I.
Gamer.
You know what her character morning? Her mom was like to her, she's so happy that she was a K-pop stan and not a gamer.
She didn't say so happy. She just said it was okay because at least I'm not a
I
gamer.
mean, she can't be both.
Yeah, but I think she's
No, but my mom would. No, my mom would rather die than raise a gamer.
You say no?
Why?
Have you seen
I don't
how
know. She just
obsessive
hates
this
people who are
is?
gamers because she thinks like they are.
We're not obsessive because we play games.
I can see that. I can see that.
It's a little bit
I can see how
stalkerish.
parents don't like games.
Did you see how she was like, some guy was hugging 1,000 people?
Okay, why are we insulting Jin's fans on this?
See?
At the countdown.
Do you see this?
The
You
countdown.
know what, though? Apparently, BTS is releasing a OST for Despicable Me 4.
Do you see this?
That's why two girls.
That's a really actually big announcement. BTS might be in the new Minions.
The movie's
I
already
thought they
out.
were drafted.
The new Minions?
Yeah.
No, it's
But
not.
one's
It's
back.
20th of June.
Yeah.
No, the
Didn't-
US
no, I
is
just
already
saw
out in the US. What the
You're
fuck are
only
you?
a reason I get BTS on my feed. I just got some, like, I'm watching memes about some dude playing the saxophone or something. Is it already out?
Yeah, because
Dude,
it's.
they're getting
No, it's
postal
not.
BTS.
It's
They're
not.
getting postal BTS.
Yeah, and you know what you're talking about. The Minions.
What?
Is that getting more?
I heard it! Don't say it
Hey
again!
Josh, did you know
I'm
there
gonna do 20 more.
free Oscar movie in cinemas right now?
Is it?
Yeah.
I'm sorry, I'm no.
Study!
No.
Bro.
Are you guys going for no.
Bro.
Yeah, I guess. Because we're here right now.
Data.
I'm trying to hold your hand from inside. Like, find your hand and like grab it.
Kakotan.
You cut it down.
I'm telling you, it's from all over my feet. I'm trying to figure out what it is.
Probably some K-pop thing.
Oh god, it was.
No, I need to find out what this means.
EMN.
No, it stands
I
for
know.
Despicable Me 4. They also have a song from Piano.
You never heard her.
Wow. I suppose some of the mentions are just
I love the BTS. I have feelings because like.
But we don't
this is
talk
nice,
about
that's
it.
true.
So therefore it's better, isn't it?
Oh, I always
Because you're
like
fucking
that.
talking about arcade. That's your fault, isn't it?
Yeah, everything is my fault.
It
It's
is.
Josh.
It
I'm
is.
gonna rewatch Arcade Season 1 now.
No, I feel like I have to rewatch it before the second season comes out, so it makes sense.
He's the
Okay,
one
we're
starting.
binge watching 8
No,
before
you're
it comes
one-
out.
I didn't bring it up. You're the one that said, oh, what are people
No, but
doing?
you're like, oh, I want to come to
Dude.
Kate. What did you say to me this morning? This entire thing came up because of you.
Yeah, I know.
End
It's
of
kind of-
conversation. Full
I
stop.
thought
I
it was really
win.
funny because it was funny.
Also, Kate
Did you hear what she said?
Full stop.
Did you hear what she said?
Why Lonnie didn't know that
Her
every
mom is
team member had to
happier, or
submit
rather,
part A,
that she be a
and he
K-pop
was
stan than
asking if it
a
would
gamer.
affect his grade, and Roseanne just said it should be fine.
That's what I'm fucking
No, you want to call my mom and ask her, did you really
Here,
say
here,
this?
here,
Actually,
here,
yeah,
here's her-
I love
here's her
calling my
digits.
mother. My mother is crazy.
Give me your mother's digits.
Come on.
I feel like the
Where is
lifestyle
your
of
mother's
people
digits?
shall be horrible.
Say that again, a little bit louder.
Yeah,
Not even
yeah,
together
yeah.
with
Your
any
mom,
relationships.
if you received your mom
Yeah, I'm
and
just
someone
saying,
in
if
match,
any
I
of
would
these
say
guys
yes.
and that's their relationship, I'm fine. If they date with a husband and after he has a girlfriend, my life is over. But everybody else I'm okay with. BTS can date whoever they want.
It should be.
And then imagine a fan that's like 2 times as dedicated as actually like you have so
The parasocial.
Yeah, she's.
Hey, Henry.
That's what I was saying this morning as well. The parasocial relationship that she has with all these people.
Wait, so he's allowed to have like a fucking cousin, like photo card?
No, he's not.
And
He's not. I'm not letting him go.
and
He's
he-
not.
Dude, I'm not fucking.
It doesn't have it.
He did have it.
I know. And when he did, I clowned the fuck out of him. It was some K-pop member because Alvin gave it to him for his birthday. So he just kept it. And every time he went home,
My wallet!
every time he went home, he would hide it so his parents didn't see it. Yeah, fucking hide it, bro.
At least I have no shame. My posters are all over my room. No one cares.
Okay.
It's like up since you were like a kid.
Caden.
No, you can fucking
Alright. How's it hard?
Oh my god, is that couple that he gave you a chicken
Alright.
Castle?
Alright, shut up real quick. Okay. So, Steel, I'm gonna go through this a little bit slower with you guys than the other guys, because the other guys have done steals. Oh wait, Dave, have you done steals?
Yeah, this thing.
Okay. But for everyone else, I'll go a bit slower. So basically, you guys aren't super used to the material properties of steel yet, essentially, right? So, basically, it's a metal, right? I mean, some of you have probably done maths, but in this course, we designed for 500 MPa steel, right? It's going to be the reinforcement for our concrete, yeah? And it's going to help us take on the tension for where concrete lacks it, essentially, right? Okay, yeah, that's its elastic modulus. You'll see that number come up a lot. So steel's not very good against fire because it melts, right? And it also isn't very good against corrosion. So when it touches the air or air with water, it will oxidize, right? And so it's actually paired up perfectly with concrete because concrete is really, like, it doesn't catch on fire. It's pretty durable against fire. And concrete will act as a protective barrier between it and the air, so it'll stop it from corroding over time as well, right? Anyway, so here's what the material curve looks like for steel. So there's a lot of things going on here, but really we only care about this region, okay? So this stuff, F you and your mum. that one's only for steel. That one's only for steel. That one's only for steel design. This one, we only care about this, which is the yield point. So you guys aren't used to this notation yet. F stands for strength for some reason. Don't ask me why. And this stands for yield. And because concrete doesn't yield, steel yields, but concrete doesn't. When you see Fy in this course, it is purely referring to the steel properties. You might also see it as Fsy, which is the yield strength of steel, but Fy also just talking about steel, right? So the idea is that this is the elastic region and this is the plastic plateau. Yep, you'll see why this matters later in the course, but we'll just leave it at that for now. So when you look at rebar on site and stuff, you'll see that it kind of has this shape. Right? Like a licorice. So why do you reckon it's like that? Basically, it's so that it binds better with concrete. Actually, it looks like that. It's kind of hard to draw. The shape. Yeah, not only the aggregate, but it'll bind better to the cement, like the paste, more surface area, etc. Stuff like that, right? Okay. Yeah, and another thing you'll notice is that we deal with class N bars most of the time in concrete design. That stands for normal ductility. But the only thing that, like, because this value won't even. Okay, yeah. That value won't matter. Okay. Yeah. So this table, what do you reckon these values mean? So N10, N12, N16. Like, why would they code it like that?
10 diameter.
Yes. So that's the diameter, right? The 10 refers to the side, like how wide your circle is, basically, right? And then N, we're designing for normal ductility. So whenever you see N10 out of context, N12, we're actually referring to the rebar.
So if we say like, let's say E10 or something like that, that's talking about now the earthquake level.
Yeah.
Okay.
But you won't see that in this course. And you probably will barely see that in Australia because we don't get many earthquakes, right? Yeah. If we're designing for Japanese standards, you might see that, or the equivalent of over there, right? But
L.
I haven't seen it in this course, and I haven't worked a design role, so I haven't seen it before. N most of the time is what you see. Okay, so let's clear up another question. So there's the nominal area and the calculated area. So do you see how sometimes the nominal area will overshoot and sometimes it will undershoot the values?
Yes.
Guess which one we designed for?
The one that
But sometimes it overshoots, sometimes it overshoots.
I mean the nominal area.
We always design for the nominal area, and that's because even though it's less geometrically accurate, it's what's specified by the manufacturer. And if something goes wrong due to the nominal area, the liability falls on them. So you always do these nice numbers. You never deal with these numbers. And if in an exam context you use the calculated area instead, you'll probably still get like 9 out of 10 marks, for example, like if it's out of that. But it's more correct to design for the nominal numbers, so keep that in mind. But you're probably not going to remember them, so just keep the table handy whenever you're doing reinforced concrete design. Essentially, it comes up quite a bit. Okay. So there's quite a few things that are going on here. So first of all, what is this? What are we looking at on the left? Yep. Correct. So which part is the concrete?
the white and black of the outside edges.
So is it that or is that concrete?
No, it's the first one.
That one's concrete, right?
Yeah.
Everything inside concrete?
No.
This?
Oh, is it? Oh, yeah. Yes, it is.
Yes. Very good. That's the first thing. So where's the steel?
The blue.
I'll do, yeah, I'll highlight all of that. That's steel, right? That's the rebar that we've been talking about.
Yeah.
So it's running in and out of the page because we're looking at a cross section, right? Okay, what's this black rectangle?
Is it
It
just
was
the?
what the guy said.
Is it just the thing that like tells you where the steel is supposed to go?
The formwork? Or
Yeah.
kind of? Not quite. It's structural.
Is it
It has a structural.
There's like another.
It's not quite the formwork. If you were to make like timber formwork, it would go outside, and that's where you would pour the concrete, right? But we don't do it in the design room.
Something about just so that the steel is completely like not exposed.
Coverage.
The cover is due to the concrete, right?
Yeah.
Okay, basically, I'll spill the beans, yeah. So, yes, very good, Sita.
Set that up.
Yeah, I'll try to remember what it was in the crash.
So so we're looking at a perspective view of, this is the axial bars, so the rebars that we've been talking about. Yeah, I'm gonna label all the terminology because there's heaps. Rio / rebar
It's like Oreo.
/ axial bars. That's what these are, right? In this cross section, they run in and out of the page. Okay. Next, we have these. Which are the shear bars? Shear bar. It's also called ligature. It's also called leagues. It's also called fitments. It's also called. I think there's another name for them. Stirrups.
Oh,
Oh, stirrups. Oh my
It's a
god.
nice object. They are like the
So there's literally 5 names. So they're all referring to the same thing. So they're the stirrups, okay? Keep that in mind. When we get to week 7, you'll learn how to design for these shear bars. They're to resist, if you remember from 1300, it's the shear force diagram forces that these ones will be resisting. Whereas these ones will be resisting for our beams, the bending moment diagram forces. Got it? Okay, so I've got a question for you. I've got a question for you guys. So, are axial bars in tension or compression? These ones, yeah?
Axial will be in tension. They're resisting the tension.
So you're saying tension, you're saying neither, you're saying
Compression.
you're saying both. So which one is it?
No,
It's compression, huh?
it's tension. Well, but I guess it depends. I remember like learning that you can either pre-stress, you can either put it in the bars in tension first or not put it.
Oh, that's pre-stressing.
Yeah.
That's
pre-stress.
This is
the
like
that's a follow-up course. I did that last time. That's a 4th year course. Don't worry about that. That's it's good that you're thinking about that. But let's think about the normal bars.
on both sides, like one side will be.
Yeah, actually, no, I kind of believe that.
Kane's on the right track. So why is that though? And
Understand.
how do you? Yeah, correct. So beams,
The top and the bottom of this.
It's because of deflections, right?
kind of. Yeah.
Like the way that the bar deflects. So like if it sags, then the bottom part will be in tension, and if it falls, then the top part.
Perfect. So this is from solid mechanics. Do you remember engineer's beam theory or Euler-Bernoulli beam theory?
That would be fine, like the neutral axis.
Yes, basically. So you have a beam, right? Like this. And when you apply forces on it, so this is a uniformly distributed load, right? It's going to deflect like that. Euler-Bernoulli, beam theory, all that. It basically says that if we take any slice of this, it's called plane sections remain plane. It's going to be a straight line, or it's just going to be the same section picture. And if we do that, our strain will look like this. Am I doing blue? Fuck. Our strain will look like this here. And if it sags like this is called sagging. This is our normal case for a beam. The top will be in compression and the bottom will be in tension. So in terms of concrete, because we know concrete rips in tension, you'll see that there'll be like tensile cracking if we have non-reinforced concrete like that, right? And these fibers will be compressed on the top as well, but those will generally be fine because concrete can resist those kind of forces, right? Got it? Okay. So, if we draw the rebar in here for this beam, the top layer, is that in compression or tension? Yes. Top's in compression and the bottom steel will be in tension. And it's because we assume in reinforced concrete design that they move perfectly together. So the strain of the concrete at this point and the strain of the steel will be at the exact same point. Does that make sense? So if we take a random slice like here, we'll see the axial bars and concrete move together at the same rate. Yeah, that's kind of all of our assumptions that we're going to carry forward into the next week of the course, which will be on flexure. Flexure is just another way of saying bending design, right? Okay, cool. So you can see sagging moments look like this, hogging moments look like this. Okay. So what I drew before was a simply supported beam, right? Where would you see hogging?
where there's point of third, there's a third, what's it called? Pin joint. Or
Yep.
joint, third joint.
Continuous beam, right? Is a continuous beam. If I draw the bending moment, right? It'll look like this. Yeah. Here you'll see negative moment in the middle above the support. That's called hogging, right? Yeah. And if I draw that section but as a beam, it'll look like this. So there'll be tension on the top side. Tension on one side and compression on the other side, right? And it would crack from this side if it was non-reinforced, right? Does that make sense? Yeah. Okay, so, another thing I wanted to allude to was cantilevers, right? Are you guys all familiar with the term cantilever? If I were to put a point load here, which way would it deflect? Okay, is the top in tension or compression? Yeah? Okay, tension. Why is that?
Because Locky spreadsheet means.
So basically the top is where you're going to see the cracking. Because if you see it flop like that, right? These fibers are going to pull apart and the compression will be on the bottom pushing together like that, right? Yeah. Okay, I want to cover one more thing this week before, because this is quite a bit. I want to cover one more thing before I have to go to 1300. And that's for you guys specifically, limit state design. So this is kind of new. Okay, basically limit state design is the first week's topic in steels. And in this week, it's like a quarter of a week's content. So they kind of already assume that you know it, right? So it looks really confusing, but it's fairly simple, right? So the idea is, yeah, again, let's go back to the tradie example, right? There's 3 tradies, right? Let's just draw it. You're designing scaffolding. There's 3 tradies, right? Which are going to represent our load on our structure, right? Say in reality they weigh 100 kilograms, give or take. How much would you pretend that they weigh in order to make this safe structural design? Oh, like all up, or I mean individually?
5% 3.
So you would kind of bump it up to some number, maybe like 125 kilograms or something, right? What about the material properties and geometric properties of the structure itself? Let's say that can take on 300 kilos exactly, strength, right? How much would you go up or down? Do you pretend it's a bit weaker or a bit stronger? So we might pretend that that can only hold 200 kilos of strength, right? So what we're doing is on either side of our structural equation, we're exaggerating the loads, the external loading, and we're underrepresenting the strength. This is safe structural design, and it's what we do in the standards. So the standards is not actually AS3600 for this, for load combinations. It's AS1170, I think. So AS1170, yeah, 0.0. You can find that through that Sigma Lectures video I fucking made, or you can just stick to the lecture slides, that's fine as well. Okay, so that's the general idea. Okay, so the real question is, how does this apply to concrete? The first topic that you're going to learn is flexure, right? So you're going to see this more next week, right? And it looks like this, the equation. Here's your factored load. And here's your capacity reduction factor. And here's your strength in bending. Right? Okay, so why, like, okay, so is everyone okay with the terminology?
Yes, man.
So, for factored loads, right, let's say we go back to basics. Let's say we go back to 1300, and it looks like this, right? And say we have a uniformly distributed load like this, yeah? Sometimes you're going to see a question presented like this, right? 200 kilonewtons, oh sorry, WG equals 200 kilonewtons or something, right? WQ equals 100 kilonewtons, okay? So what do you think that means? Yes. So basically G represents your dead loads and Q represents your live loads. So a dead load is something that's there permanently. And there's actually two types of dead loads, yeah? Usually you call the total dead load just G, or GT sometimes is total. There's GS, which is dead load due to self-weight. That's just due to the density of the actual material, right? And we have GP, which is dead load due to partitions. So partitions are things that are like there, and you assume they don't move for the duration of the entire structure, right? So for example, pretend this podium is immovable. That's not part of the structure itself, but it's something that's loaded there and is not going to move for 100 years or whatever we're designing for. That's a partition. So live load is usually due to humans or anything that moves around and will vary heavily over the duration of its lifetime, right? So here I've said there's a distributed load of 100 kilonewtons due to live loading, and then there's a dead load of 200 kilonewtons, right? So the real question is, how do we account for all these forces? Well, we're going to do the worst case scenario, right? In concrete design, there's exactly two scenarios we account for. Because in concrete, unlike steel, we don't care about wind, and we don't care about earthquake design, at least in this course, right? Anything like that, right? We don't care about earthquake design for steel either. But in steels, we care about wind and stuff. In this course, it's just dead load and live loads. And so there's literally only two combinations, right? There's only due to dead load, and there's dead and live load. These are our two combinations, and the one that ends up being bigger is what we end up taking as the worst case scenario for our loading. So that's the left-hand side. So what M is literally the bending moment. So we draw the bending moment diagram for both loading cases. Right? For a simply supported beam, where's the highest moment going to be? In the middle. So we're going to draw two bending moment diagrams, and you're going to find that one's going to be bigger than the other. You're going to find that the live and dead load is going to be bigger. No, because sometimes the live load might only go to the side like that, and it might be really trivial. And in that case, your dead load only will be a worse loading case. But in the question, they'll always provide you with all the information you need from the free body diagram. In terms of the strength and bending, that takes more time to explain, and that's what we'll go over next week. But that's the actual material and geometric properties strength. And we're going to use engineer's beam theory and stuff like that. Capacity reduction factor, this comes from AS 3600 as well. And it depends on the type of loading action that we have. In flexure, you're going to find it's going to be between 0.85 and 0.65. Okay, that's it. All right. I'll send you guys this page. This page in particular is not in my notes, but it's better than my notes that I currently have.